So in this slide, we reiterate the end of the previous example we were solving with Taylor series, where this is just the representation again of the error for using that fourth order method. And again, that's what this is right here. And again, we were given an initial condition on the initial solution, the solution y at 0, so that we could derive an expression for what the fourth derivative at 0 would be, which was 248. And because we did one integration step, we can actually evaluate now the fourth derivative of the function at 0.1 by using the same equations that we came up with to derive expressions for the higher order derivatives given the original ODE. And again, what we came up with is that the estimated error is something around negative 6.8 times 10 to the minus 5. And using the analytical solution, the actual value should be this. So then again, what we see is that this was our approximation right here for the solution at 0.1. This value, of course, is the actual result, what it should have been. So the error is really just this particular value, negative 7.7 times 10 to the minus 5, which is fairly reflective of the truncated error representation using for the fourth order Taylor series method. So what it's telling us is that we can trust that error estimate, and that's a very reliable aspect of using the Taylor series method, is that you can trust those error estimates, albeit that they can be costly because you may have to have many functional evaluations to get up to higher order derivative approximations. But then again, it's very nice that you know when you can stop. So now we're moving on to another approach for solving first order ODEs, or systems of first order ODEs. And it's to play upon the fact that sometimes, because you have to do repeated differentiation with Taylor series, it's easy for a human to get the formulas wrong, so that can be very error prone, and it is obviously tedious to get those expressions for those derivatives using the original ODE. So Runge-Kutta methods, that's how you say this. So a Runge-Kutta method is a method designed to eliminate this need for repeated differentiation of the ODE itself to get those higher order representations for Taylor series. A first order Runge-Kutta method is actually equivalent to the first order Taylor series integration. So this method right here, which would truncate Taylor series very quickly, is actually what technically is called a first order Runge-Kutta method. It's just advancing the solution from x to x plus h using the derivative multiplied by h, but then we realize, of course, that the ODE itself gives us the ability to represent that derivative, because this term right here is given by the ODE. So the f of x, y term represented here is coming from the ODE itself, because it's framed in the form of the ODE being y prime equals f of x comma y. This is vector valued, and this is vector valued. So again, the ODE itself helps us construct this integration step. So the first method we're going to consider of a Runge-Kutta nature is called Euler's method, and it has a wonderful graphical representation, which is the reason we're looking at a picture right now, looking at this graph. And we want to make sure we understand this graph, because it actually helps us, in a sense, derive the method. Even if we were to forget the equations, we could actually derive it by just understanding the meaning of this diagram. So we have a Cartesian system here. The x-axis is represented certainly at the bottom, and what we have here on the y-axis is actually not the y, it's the derivative. So what we're doing is we're graphing the derivative. Remember, keep in mind the original ODE is of the form y prime of x equals f of xy. And what we're drawing, of course, is a representation of that ODE. So again, y prime is equal to f. If we're thinking of only x as a function of only one variable y, it lives in, it's just one dimensional in this case, it depends only on x. So what we have here is a drawing of f of xy because it specifies the derivative as x moves on the x-axis, all right, with corresponding values of y. So the task, of course, is to estimate what the solution is doing at x plus h. That's always our goal here, is given what we know of y at x, what would it be at x plus h? So if you think about looking at the area here under the curve, one way of looking at the difference between y at x plus h versus y of x would be actually to integrate this f of x function when f of x is evaluated at x and then x moves to x plus h, because that would describe the derivative moving from x to x plus h. So if you took the derivative, if you took the integral of that derivative, you would be explaining what the solution is doing between x and x plus h. So that's what we've represented here, that the area under that curve, the green curve there, would represent your solution moving from x to x plus h. And then realizing the fact that, well, we have an expression for the derivative, and that expression for the derivative is given by this f of x comma y, because that came from the ODE. So the ordinary differential equation tells us a representation of the derivative in terms of x and y. And so what Euler method basically does is we're going to estimate that area. So just think the same way we did with numerical integration. This is basically what we're doing to solve an ODE, is integrating, is we want the area under the curve, but without relying on information on higher order derivatives, we're simply going to use the fact that we know what the solution is doing at y equals x. So we're using this particular value here of what y is at x for that curve f of xy, right? In the sense that the yellow shaded region there, whose height is f of xy, so this height right here is f of xy, and this length right here is just h, correct? So we would just multiply h times f of xy, whatever that value is, and we get this box, and use it as an estimate of the area under that green curve from x to x plus h. Now you may say, well, gosh, that looks like it's not a very good approximation. Well, that's going to depend on the shape of that curve, right? If that derivative is kind of constant, then it's actually a very excellent approximation to the derivative. So the truncation area here is that gap between what that box is versus the total area under the curve, under the green curve. And we're hoping, and it turns out you can show, that that truncation area is proportional to the slope of that curve, which would actually be the second derivative. So the slope of that curve, the rate of change of that curve, and you know that would be the derivative of the derivative in this case. So keep in mind, we're actually drawing the derivative. So it's just basically using the fundamental theorem of calculus that if I want the original solution given the derivative, I would have to integrate. And we're exploiting the ODE to represent what that derivative is doing. It's just we have to decide how often we want to sample it, how often we want to sample that right-hand side, f of xy. In this case, we're just sampling at when x, the initial part of the integral at x versus x plus h. And that's the derivation of Euler's method. So it's just going to be multiplying f of xy times h to get an estimate for that area under the curve. So the complete method would be y of x plus h equals y of x plus this f of xy times h. And we'll see that on the next slide. That's Euler's method. Basically, again, written as a vector valued function for y, which y could be in multiple dimensions, not just one. But for now, we're going to do it in one dimension for this next problem, but that's simply what Euler's method is. And again, we know that y prime of x is the same thing of x, f of x on the y. And the sample problem we're going to do is on page 251, 252 is example 7.2. Going to solve a second order ODE, y double prime minus 0.1 y prime minus x, given the two initial conditions. So this is again an IVP because it involves the initial conditions at the same point for the solution and its derivative. If you had a third order equation, then you'd have to have another initial condition for the second derivative. So you go up to one derivative less than what you see in the equation itself. And we're going to solve it from 0 to 2 with increments of 0.5. So that's just the steps size that we're going to take to march our way from x being 0 all the way to 2. And we're going to march using Euler's method. And it's just handy to know that this particular second order ODE has an analytical solution. It involves an exponential e to the minus 0.1x. And we can use that to see how well we're doing in terms of using Euler's method to approximate it. Perhaps before we move to the example to set it up and use the code, we'll look at the code, the Euler.py file, which is on pages 248 and 249 of your book. So if we take a look at the Euler module that's described in the textbook, again, on pages 248 and 249, you can see that it assumes that the user is going to supply a function capital F of xy that specifies the differential equation. The assumption is that that the function can handle any number of first-order differential equations. So if you are solving a second-order equation, as we are, we have to convert it to a set of, or system of first-order differential equations, which we'll do in just a second for the example problem we're going to look at. But that's the specification, is that you would have converted, whether it be, regardless of the order of the differential equation, you'll convert it to a set of first-order equations. And you need a function, capital F, to basically return the appropriate right-hand side for each of those first-order differential equations. So the module is indicated here. Euler returns the arrays x and y that contains the values of x and the corresponding solution y at intervals h. So there's the step size h, there's x and y, and a stopping value, the last value of x that you're going to integrate to, called x stop. And this just simply implements Euler's method. If we continue on to the next page, again, the user has to supply the capital F function that describes the right-hand sides of all the first-order ODEs. The problem, and just using arrays, it simply just goes through a while loop while x is less than x stop to implement Euler's method indicated there as y gets y plus h times f of xy. Increment the x, append the current approximation of y and the current x value of x into the larger arrays x and y, and return them indicated here using, again, the NumPy module function array to convert the list. You're actually going to use two lists x and y and append each new value of x and y to the list, and then return appropriate arrays. So we indicated before that the function's returning arrays, so we'll be using the NumPy array function inside to do the return. Before we move on, there is another very useful function that will be used for these Runge-Kutta type methods, and it's called print solution. It's just a way of getting certain values of those x and y arrays printed out as you're integrating from an initial value for your IVP problem to some distant x, you may not want every single step, the approximation of the solution y at every single step. It depends on how h is. If h was 1 over 100th and you were integrating from 0 to 1, you would have over 100 elements there, and you may not want that many. So what you can do is specify with this parameter frequency f or FREQ the frequency at which you'd like to have the results printed. So it's just printing out a nice little tabular output down here, and it just determines the frequency of how many elements you want to print out. The example is indicated if frequency is equal to 5, then every 5th integration step would be displayed. You set frequent equals 0 only if the initial and the final values are shown, and you get nothing in between. So it's just a nice way of seeing what the outputs are, and we'll use it in our coming example. So if we move to page 251, here's the example we're looking at. Again, we'll go back to the lecture slides in a second, but you have a second order differential equation, y double prime equals minus 0.1 y prime minus x. These are the two initial conditions that you have. Initial IVP problems, again, are specifying at one particular point all derivatives and the solution. In this case, we're indicating the solution is 0 when x is 0, and the derivative starts at 1 when x is equal to 0. The goal is to integrate from 0 to 2 using Euler's method, and the step size, fairly small, is 0.05, and they want you to plot the computed y together with the analytical solution, because it turns out, a la the methods of Math 231, this is actually what the analytical solution is. Keep in mind, though, the power of doing these numerical approximations is you can do them regardless, even if you don't know what the analytical solution is. So remember, the user is going to provide this capital F of x function for the Euler's method to integrate, and it has to provide the right-hand sides for both of the first-order ODE equations. So you have to convert this second-order equation to a set of first orders, and that's easy to do with letting y prime of 0 equal y1, and then y prime will be equal to negative 0.1 y1 minus x, where again you've just made the variable substitution that y1 is equal to the derivative of y0, and so that's using the same simple transformation we had before. And the initial condition would be the vector would be 0, 1, because we were given that y0 equals 0. Well, that's the value of y0, and y prime of 0 equals 1. That 1 is the value of y1, the new variable y1 at 0. And the code to solve the problem is indicated. It's fairly straightforward. Your user has to build this function capital F of xy. You just use the fact that you've determined what each row should look like. So f0 should return f bracket of 1, and f bracket of 1 should be negative 0.1 times y bracket 1 minus x. Okay, and we initialize f to just be a simple array of zeros, a list of zeros in this case. So, so f is just returning a list of both of those values for the first row, the first set of the results for the first first order differential equation, and then the second. Again, you convert the second order ODE into a set of first orders, and this is when you have y prime of 0 equals something and y1 prime equals something, and then continue on depending upon the order. You'll have 2 rows for a second order differential equation. You'll have 3 rows for a third order, and so forth. So that's how you know if you've done it correctly. And again, you're just making a very simple change of variables, in this case to let y0 be y, and let y1 be the derivative of y0, and so forth. Okay. So if we look at the rest of this code for solving the 7.2 example, specifying that we're starting our integration at the initial value of x equals 0, we're stopping when we get to 2. We create a very simple array of the initial values of y, which are just 0 and 1, as we indicated up here. Set the step size to 0.05, and then actually call the function to do the integration. And it's actually called integrate here, f x y x stop h. Okay, so this is going to use and implement the Euler's method, which is simply first order Runge-Kutta method, and return the arrays x and y with all the appropriate values of x and y. When we stepped from 0 to 2 in increments of 0.05, here's the exact solution, which takes the x's that are returning by the integrate function, and we'll just apply this formula here, which is based on the exact solution, and get all those values, and then plot both the exact and what we've approximated. And the book also gives you a picture to illustrate that the numerical values are here with these dots, and the exact value is here, and you're getting some separation a little bit past x equals 1, but for the most part it does pretty well in approximating the solution there. So the truncation error is proportional to the second derivative, and so there is some separation here because the curvature, once that curvature starts increasing like this, then so does the error. So that's one reason you know, why that separation is there between the true solution and the approximated one. One idea might be, you know, reduce the h a little bit, and maybe we can drop the error a little bit. So let's look at the code, but before we do that again, let's go back to our notes just so we again indicate the problem at hand. We're solving this particular second order IVP problem, and this is the exact solution. This is Euler's method, which we're using, and so we must convert the second order ODE into a set of first order differential equations. We do that with this standard substitution. Start off with y0 being y, and then let y1 be y prime, and so forth. Let y, if you had a third order, then the next substitution would be y2 equals y double prime, and so forth. And just by definition, we know that, well, if y0 is y, then y0 prime is y prime, but that's the same thing as y1. And if we take the derivative of y1, we get y double prime, and that is given by the second order, that's given by the original ODE. Let's look at the code called example 7_2.py, and I'm going to provide this module as well as the Euler code for you to be able to do this problem. So you'll see, number one, that you're using NumPy because you're needing arrays. Print solution is available if we want to see the solution. We'll be using it for some other problems in the chapter. We're using the Euler module, which I'll again make available to you, and we're importing all the functions, one of them being integrate is one of them. That is one thing that is a little troublesome, I suppose, is that the functions are always called integrate in this, for these ODE methods, regardless of the module. So, well, be that as it may, we're also going to use Matplotlib to graph our solutions. Again, user has started off by, once we have our second order differential equation, we need to convert it to a set of first order. So that's very, very important to be able to do that with those variable substitutions. So we have it. We have our first row and our second row for our f of x, y. And the rest of the code is just as illustrated in the book, very straightforward. Call the Euler method to integrate from x to x stop from 0 to 2, increments of 0.05, and take the array x that's coming out, and we can generate all the exact values. And if you think about it, this is really cool because this one line basically is the equivalent of a loop in most languages. we're just taking all the values of x, multiplying by 100, and then again subtracting this particular function. It's just evaluating that entire function with all the array values simultaneously. So think about that. I mean, x is a whole array of values, and now we're getting what the value of the exact solution is at every single one of those values by sort of embedding that array x into that expression for the analytical solution. So that's pretty powerful there. So let's go ahead and run the code as we have it here for this particular problem. Since we're using Matplotlib, it'll pop up the solution. I'll move this over into the window so you can see it all. And indeed, we're getting some separation where the curvature starts increasing, and that because the truncation error is proportional to it. But this pretty much matches what we saw in the book. And again, as suggested, one thing we might try to do is to go back and maybe if we decrease that step size just a tad, maybe the error would drop a little bit. So let's just half it. So now we're using a very small step size and just simply rerun the same code. We're still integrating from 0 to 2, but we're taking a much finer step. And what this graph indicates is that it pretty much matches it. It's because the dots now are very hard to distinguish because there's so many of them, but it almost matches exactly to what the analytical solution is. So, and again, I'll put this code on Blackboard and you can play with it a little bit to see the effects of choosing different H's. So that's Euler's method, basically a first-order Runge-Kutta method. And we're going to, in the next lecture, we're going to generalize this for deriving a couple of other methods similar to Euler's method, but hopefully in ways that might have a little bit more accuracy than what we're seeing right now, with the truncation error of Euler being proportional to the second derivative. You know, perhaps we can improve upon that error with some other similar related methods.